Each year, oceans produce half of our oxygen. They represent nearly 1/2 of the productivity of the planet, and they are threatened. We know that by producing ever-increasing amounts of CO2, man is turning the climate upside down. Very recently, we've also learned the excess of carbon dioxide in the atmosphere modifies the chemistry of the deep seas. Oceans are getting more acidic. Their acidification leads us on an uncertain journey about which the scientific community is worried. It's a very special polar adventure indeed, which leads the Esperanza to sail on this 6.5 million square mile ocean, half of which is nothing but ice throughout the year. For 7 weeks, the Arctic Ocean is going to be a laboratory for 35 scientists, who have come to observe the impact of a phenomenon which has only very recently started to be observed, the acidification of the ocean. The international scientific base at Ny-Ålesund, northwest of Spitsbergen, is only 750 miles away from the magnetic pole. It's here that for the very first time, and under the initiative of the European research project EPOCA, more than 100 scientists from 9 countries and 29 organizations will gather around the first research program on acidification. Jean-Pierre Gattuso from the French Oceanic Laboratory of Villefranche-sur-Mer is the coordinator of the project. Ulf Riebsel from the German laboratory of IFM Geomar in Kiel is the scientific manager of this experiment.
C'est un challenge pour la science parce qu'on est les premiers en fait à travailler sur l'impact de l'acidification dans les eaux froides et dans des milieux extrêmes comme ici. L'acidification des océans en fait est un processus que l'on connaît depuis longtemps. On sait depuis une trentaine d'années que lorsque du gaz carbonique est absorbé par l'océan, il rend l'océan un petit peu plus acide. Mais il n'y a qu'une quinzaine d'années qu'on a réalisé que cette augmentation d'acidité aurait un impact sur les organismes et les écosystèmes marins.
Carbon dioxide produced by humans is modifying the chemistry of the deep sea, even in this remote and icy universe.
On pense que l'Arctique va être une des zones qui va être touchée la première par l'acidification des océans. La raison est très simple, c'est que tous les gaz, y compris donc le gaz carbonique, se dissolvent plus facilement dans l'eau froide que dans l'eau chaude. Et donc dans l'océan Arctique et aussi dans l'océan austral, on part déjà avec un niveau d'acidité qui est relativement plus élevé que dans les zones tempérées et chaudes.
To study the reaction of marine organisms to our ever-increasing emissions of carbon dioxide, CO2, researchers are going to install these 55-foot-high metal cylinders called mesocosms in the fjord.
Launch it after, yeah.
It's taken 4 years for the German scientists of the Oceanographic Laboratory in Kiel to conceive and build these enormous test tubes. All sorts of languages are spoken on the wharf. Technicians and researchers are all bustling around. Within 1 week, the mesocosms must be anchored in the waters of the fjord at a freezing temperature of 33 degrees Fahrenheit.
Once it's in the water, we'll then lower the bags to the full depth, which goes then 15 meters into the water, and by sinking down it will just cut out a full column of water with all the organisms included in it. And once it has enclosed this body of water, 55,000 liters of water with many thousands of organisms in there, we'll close the bottom and then we can start manipulating the system by adding CO2. And we'll just have the different mesocosms, each of one representing a different time in the future. So we go 20 years into the future, 40 years, 60 years, 80 years, whatever we project in terms of CO2 rising in the atmosphere. And then we'll just, once we have that manipulated, we'll just watch it. Es ist eine Mischung aus Begeisterung. Ich bin begeistert, dass es losgeht, aber ich habe auch Angst, dass Dinge schiefgehen können. Wenn es jetzt irgendwie nicht klappen sollte, dann haben wir wirklich sehr viel Energie hineingesteckt in ein Projekt, ohne dass wir dann den Erfolg am Ende haben. Also es ist eine Mischung aus Freude und Angst.
In front of GMO1. GMO1. So we have our own little lunch break here on the ship with nice chocolate bars and wait for you. Okay, we're having a proper lunch, so enjoy.
We're just putting on what we call the tents, and the purpose of those tents is to not have seagulls fly into the mesocosms, because as they poop in there, of course, they bring in a lot of nutrients, which would then interfere with our experiment. The biggest threat we have is the ice. We can handle small pieces of ice, we can push that with our boat, but if it comes in a massive wall of ice just crossing our location here, there's little we can do about it.
At the moment we are filling this tank about 1.5 cubic meters with seawater, with natural seawater, which we pump from the fjord. And later on, when this tank is filled, we will aerate that water with CO2 gas. And by that we will acidify the water, really saturate it with CO2, and then use that water to inject it into our mesocosms. We do this to simulate future changes in ocean chemistry, especially ocean pH.
pH is a measure of hydrogen ion concentration. This is the universal index of water acidity. It's the pH value which shows the acidity or basicity of the water.
Une eau acide a un pH inférieur à 7. L'eau de mer a un pH qui est aux alentours de 8, donc elle n'est pas acide, elle est le contraire, elle est basique. Cependant, lorsque cette eau de mer absorbe du gaz carbonique, son acidité augmente, c'est-à-dire qu'on va vers des pH plus faibles. On pourrait prendre une analogie avec la température. Si par exemple dans l'Arctique, en hiver, il y a une température de moins 40 degrés, et puis le lendemain, il y a un événement météorologique, et on monte à une température de moins 20 degrés. On dira que la température s'est réchauffée, pourtant la température est toujours froide. Eh bien c'est pareil avec l'acidification des océans. On va vers un océan qui s'acidifie, mais il ne deviendra jamais acide, son pH ne deviendra jamais inférieur à 7.
The stability of pH depends on the level of emissions of carbon dioxide, one of the most significant greenhouse effect gases. Oceans play a major role in the regulation of the cycle of CO2. When CO2 circulates freely between all the various components of life, atmosphere, soils, plants and oceans, marine organisms are able to come to a natural balance with the gas. But when it penetrates the oceans in too great a quantity, CO2 may bring death to the deep seas.
When carbon dioxide dissolves in water, when it's taken up from the atmosphere into the ocean, what happens is it forms carbonic acid. CO2 reacts with water to form carbonic acid. Unlike all other gases, oxygen and nitrogen and argon and so on, they dissolve in seawater, they don't react further with water. CO2 reacts with water and forms carbonic acid. The more CO2 enters the surface ocean, the more acidity we have in the water. This is in fact the process of ocean acidification.
Once it's been absorbed by surface waters, CO2 continues its route towards the depths of the ocean.
In the surface waters that receive the sunlight, you have algae, planktonic organisms that produce organic matter. This organic matter is then eaten by other organisms. So you have a whole food web here. And at the end, carbon is being transported to the deep. So it sinks down, and together with the organic carbon, we also have a sinking of planktonic organisms such as foraminifera, diatoms, and they have skeletons that fossilize. This whole process is called biological pump, and it basically consists of two words: biology, that's what's driving it, and a pump, because we are pumping carbon against its gradient to the deep sea. So there is more carbon in the deep sea than there is in the surface. That's why, in fact, without the biological pump, the PCO2 in the atmosphere would double within 200 years. So the biological pump plays an important role in controlling the PCO2 in the atmosphere.
The equilibrium has been threatened ever since the Industrial Revolution began. Within 200 years, oceans have absorbed 500 billion tons of CO2, equivalent to 1/3 of all emissions produced by humans. As a consequence, acidity of water has risen by 26% in the same time span. Our planet has already known such events of acidification of the oceans, but never to this extent and at this sort of rate.
Today we are much more efficient than the natural system was 55 million years ago. It is estimated that there was about, say, an emission of CO2 of about 3,000 gigatons over 5,000 years. That boils down to a rate of about 2 to 3 gigatons per year. Well, today we are producing 30 gigatons a year. So we are about 10 times faster. And that is what it's all about. That is where scientists are worried about. It's the rate of the carbon perturbation today. Which means that the impacts may be way stronger than we have ever seen in Earth history.
It's the scope and nature of this impact during this century that researchers are studying at Ny-Ålesund. They want to know how marine organisms react and adapt.
The main focus of our study here is the planktonic community. So we look at bacterioplankton, at the phytoplankton, the small microalgae. We look at the zooplankton. And of course we're interested in the interaction. How does ocean acidification affect their interaction? Does it make them sensitive to certain processes? Viral attack, for example, is an important issue that we look at. The availability and the quality of food that is provided to the zooplankton is an important aspect.
The increase in acidity reduces the amount of carbonate ions in the ocean. A great number of organisms need these ions to build their shells and their skeletons of calcium carbonate. But when water becomes corrosive, it attacks the shells. To measure the impact of the phenomenon, researchers are going to inject various concentrations of CO2 into the mesocosms.
Can you bring us the weapon before you go? Are you done on that side? Yes. Good. We are simulating the future in terms of CO2 conditions in the mesocosms. So we're adding CO2 enriched water, and this one, for example, will be 30 years from present, the next one will be 60 years from present. So we reach the CO2 levels that we expect, that we project for the future.
To carry out this extremely precise operation, the German scientists have invented this star with just under 100 branches, which allows them to distribute the CO2 evenly throughout the water column.
Das war CO2. These are the first bottles, CO2 enriched water, that we add. And initially we add now 50 liters. For the first 50 liters, the increase in CO2 and the decrease in pH is small, because now the ocean has a strong buffer capacity. It can take a lot of CO2. As we go the next step, for the same amount of CO2 enriched water, the step is higher. We go the next step, higher, because the buffer capacity of the ocean goes down and down and down. So the same amount of CO2 makes a much bigger change in pH in the future.
runter.
One question we have is if there's more CO2 in the water, do the organisms use more CO2? Do they take up more through photosynthesis? And then the next step, of course, is, well, if they take up more, where does it go? Who benefits from the extra carbon? So by tracing the carbon-13, we can then say, okay, it goes into bacteria, it goes into zooplankton, it goes into DOC, whatever. We can find out.
It's the impact of acidification on future oceans which is being studied. At Bremerhaven in Germany, it's the past that's being explored. Using sample cores of sediments of fossilized marine organisms collected from up to 10,000 feet deep, the chemical evolution of oceans can be studied over millions of years.
So now we have put these archive cores together, and we go from the old part, which is deeper in the sediment, to the younger part. And you can see that the color is changing from darker to a lighter section over here, because it contains more calcium carbonate. And that tells us that the climate was more suitable for these organisms at that point. And that's what you can read in the sediment cores. And you can sample those and then again look at the chemistry of the organisms, and that's where we learn a lot. The geochemistry of the organisms tells us something about the temperature, about salinity, about productivity, and about pH of the ocean. Today we are so efficient in producing CO2 that the buffer capacity of the oceans is outstripped. And this is something that we try to look for in sediment cores as well, so that it's not just something that's happening today. It has happened in Earth history. It has happened at the end of the Permian, about 251 million years ago. It has happened at the Paleocene-Eocene boundary, about 55 million years ago. And we see fingerprints of ocean acidification in those epochs.
It was at that time intense volcanic activity which caused an excess of CO2. Numerous marine species had disappeared then, such as Foraminifera, a group of calciferous plankton, whose reaction to acidity is now observed, comparing it to what happened millions of years ago.
We have noticed that even during the glacial interglacial transitions, where you have a change in the carbonate chemistry of the ocean, that the planktonic foraminifera are getting thinner when the oceans are getting a little bit more acid. So the thickness of the shell is impacted by ocean acidification. We are diving to collect foraminifera as juveniles. Here you see a small planktic foraminifera, and you see the symbionts all around it. Those are dinoflagellates. They have spines. They use their spines to collect food. We feed them until they are adult. So we are growing them at different pH, at different carbonate ion, and look how these conditions impact not only the chemistry of the shell, but also the morphology, the thickness, the ultrastructure of the shell, to understand what the consequences are ongoing ocean acidification have on these organisms.
Consequences are more especially expected in organisms whose shell or skeleton are made of two forms of calcium carbonate, calcite and aragonite. Aragonite is the most susceptible to dissolving, and organisms using aragonite as one of their components will therefore be the most affected by acidification.
Plusieurs grands groupes d'organismes ont de l'aragonite, dont les coraux tropicaux qui fabriquent des récifs coralliens et des ptéropodes, des petits organismes, des petits mollusques qui nagent dans l'eau. Ça ressemble en fait à un escargot, et cet escargot donc, a une coquille qui est enroulée. Cette coquille est faite d'aragonite. Et donc coraux et ptéropodes qui sont fabriqués en aragonite sont plus vulnérables à cette corrosivité de l'eau de mer.
Experiments have been carried out in laboratories such as the one in Villefranche-sur-Mer, where Jean-Pierre Gattuso is a research professor, which confirmed that the acidity of the water has an impact on calcification and on the growth of calciferous species such as pteropods. In this bay of the Côte d'Azur, renowned for its nearby deep waters, researchers have been measuring the chemical and physical parameters of seawater for 50 years. The abundance and diversity of planktons are exceptional here. Less than 10 minutes away from the laboratory, researchers can collect the samples they need, including the pteropods.
Yves, t'en as assez ou pas? C'est des petits mollusques planctoniques, des petits escargots de mer. Ce sont les petits bâtonnets qu'on voit ici au fond du seau. Il y en a une petite centaine.
Pourquoi vous cherchez ça particulièrement?
Parce qu'ils sont très importants pour la chaîne alimentaire et on pense qu'ils vont être beaucoup affectés par l'acidification des océans.
Ils ont quel rôle en fait?
C'est une source de nourriture importante pour les poissons notamment, les baleines aussi selon les régions et quelques oiseaux marins également. Je suis en train de collecter donc les ptéropodes qu'on a récoltés ce matin et je les transfère dans un bain de calcéine. C'est un marqueur fluorescent qui va se fixer à la coquille des ptéropodes. Ils ont une coquille externe qui leur sert de squelette, qui les protège face à l'environnement. Et donc cette coquille va sûrement être affectée par l'acidification des océans. Donc nous, ce qu'on essaie de voir, c'est l'effet d'une diminution du pH sur la formation de cette coquille.
Ça joue sur leur flottabilité ou pas?
Oui, ça joue sur leur flottabilité, donc ça leur sert de ballast notamment, parce que ce sont des animaux qui font de grandes migrations verticales, donc plusieurs centaines de mètres par jour. Et c'est également un rôle de stabilisateur. C'est une technique donc, où on va mesurer vraiment l'extension de la coquille. Donc pour ça, il faut quand même attendre au moins quelques jours donc, pour qu'on puisse vraiment mesurer la croissance de la coquille des ptéropodes. Donc au bout d'environ 5 jours, on peut déjà voir les effets du pH. C'est vraiment violent, c'est vraiment une réaction chimique qui se fait quasiment instantanément. Donc ça bloque vraiment le mécanisme de calcification des ptéropodes. Ça le ralentit tout au moins beaucoup.
Eux, ils pourraient pas survivre à l'acidification, les ptéropodes?
On ne sait pas s'ils peuvent survivre ou pas, ça dépendra beaucoup des régions océaniques, étant donné qu'il y a des régions qui sont plus ou moins exposées à l'acidification. Il y a sûrement, selon les espèces également, donc on peut aussi imaginer peut-être que les ptéropodes vont réussir à s'adapter ou à survivre sans coquille.
C'est le cas, donc ça a été montré dans une expérience qu'on a fait. On a réussi à garder des ptéropodes en vie sans coquilles. Mais en revanche, dans l'écosystème naturel, on peut imaginer qu'ils seront beaucoup plus soumis à la pression des prédateurs. Donc malgré tout, ça a engendré de grands bouleversements.
Dans le domaine de l'acidification, il y a beaucoup d'incertitudes, mais il y a quelques certitudes. Parmi les certitudes, c'est que l'acidification est un processus qui est indéniable, qui existe et qu'on peut mesurer. Je pense que 9 publications sur 10 concernant l'impact de l'acidification sur la calcification des organismes, 9 publications sur 10 montrent qu'il y a un impact négatif. Il existe quelques espèces, notamment une que nous avons étudiée ici en Méditerranée, qui ne semble pas affectée par l'acidification. Donc il y a des mécanismes qu'on ne comprend pas aujourd'hui, on ne sait pas pourquoi certaines espèces sont résistantes, et la majorité ne le sont pas, mais il y a encore beaucoup de recherches à faire dans ce domaine.
The island of Ischia, north of the Gulf of Naples, is one of the few sites in the world where one can observe the increased impact of the acidity of seawater on the ecosystem.
This is a good natural laboratory for our scientific studies because CO2 is coming up in large amounts over a wide area, so we can see the effects of carbon dioxide on lots of marine communities, on rock